listen-only mode.
Hello, and welcome to Measuring Color, the second installment of Data Color's Color Competence webinar series for busy color professionals.
I'm Kenny Thomas, here with my colleague Phil Ruggiero. Today, we'll see how variations in samples, environment, and instrument design affect color measurement. So you'll learn measurement options and techniques appropriate to your product and goals.
Your comments and questions are welcome during the session. Just type them into the GoToWebinar control panel anytime. Kenny and I will answer them at the end. You ready? Let's go.
All right. In the first webinar of this series, we examined the subjective nature of color perception and visual evaluation. Today, we'll look at objective measurements, instruments, and object properties affecting colorimetry, the science of quantifying and physically describing that human color perception. Unlike a perception, color measurement is an exercise in reduction. We break apart the color experience into measurable quantities of energy, light from a source, light reflected or transmitted by an object, and data from color matching experiments defining a standard human response.
In the end, we reassemble those numbers into an analog of the color experience, a measurement of color. Obviously, effective measurement requires controlling many of the same details as good visual evaluation, but the hardware differs. Differences in color measurement instruments bring their own advantages and limitations. Knowing the possibilities and options give you the power to choose, to create agreement between instrumental and visual methods or not, and to take advantage of the best of both. Many material properties affect appearance and color. Haze, opacity, surface effects like texture and gloss. With instrumental evaluation, their effect or detection varies with different instrument designs. There's still things to consider in any evaluation, but it will help your evaluations to learn which are included in instrument evaluations for specific instruments and which aren't. Light is vital to colorimetry. It's the thing that's measured. In our first session, we said no light, no color. Today we say no light, no measurement. Well, other than zero, and that's not very interesting. These graphs come from spectral measurements of energy output across the visual spectrum from various lamps. Like passing white light through a prism into a rainbow, spectrometers let us see how different lamps vary in the amounts and colors of the light they produce. The CIE, the International Commission on Illumination, specifies standard numbers for light sources. They're called illuminants. They're scaled to allow comparison of different sources. It's the standardization that's the benefit. Actual lamps can vary, and they do, and be judged by how well they correspond to established illuminants. The differentiation is important here. There's a source, and there's an illuminant. An illuminant's a table of numbers. A source is something you can turn on and off. The human response is also reduced to numbers. The CIE specifies standard observers, statistical measures based on color matching experiments with 3 primary colored lamps. There are 2 CIE standard observers, one for evaluating smaller areas and another for larger, for exactly the same reason that small color patches appear differently colored from larger ones. The human retina is not uniformly populated with light-sensitive cells. Let's take a look at some color measurement instruments.
Well, here are some old ones. That comic from 1965, comic was short for colorant mixture computer. It was an analog computer for recipe prediction. Notice how the size of the spectrophotometers have changed over the years too. And some new ones here. Datacolor's new viewport for image-based colorimetry, and the 45G, a portable spectro with amazing inter-instrument agreement. The 650 is our flagship benchtop spectro with all the options. They're great instruments. Of course, I'm proud and I wanted to show them to you, but I picked them for another reason too. They're all different designs, each having strengths compared to others. Here are some basic categories for instruments used in colorimetry. They still hold true, I suppose, but advances in technology are blurring the lines. The difference between a colorimeter and a spectrophotometer is an example. The data color viewport is a bit of both, but not much like the classic versions of either. Discussing modern color measurement options, it'll help to know the distinction and relationship of some terms. Spectroscopy is measurement of radiation intensity. Spectrometry is measurement of a specific band of radiation, visible light. Colorimetry is measuring visible light with a specific intention, correlation to that color perception. The distinction among measuring devices, spectrometers, spectrophotometers, and colorimeters, is based on intention and use.
Here's a simple schematic of a colorimeter. There is a lamp, a place to put the sample, a lens to capture and focus the light on a detector. In front of the detector are three filters, trichromatic, based on three primary colors, like human vision is. Classic colorimeters report color coordinates directly, specific to the light source and filters used in the instrument. This is a schematic for a spectrophotometer. It looks similar, except the spectro has a different device between the lens and detector, a monochromator, to spread the light into separate wavelengths with much finer resolution than a few filters. In this picture, a prism replaces the colorimeter's filters. Modern spectros use fancier things like a holographic grating, the equivalent of tens or hundreds of filters giving unique measurements across the visible spectrum. The spectrophotometer reports light reflected or transmitted by a sample as a percentage of the light striking the sample. Spectrophotometric measurements are relatively independent of the light source or the observer. Spectrophotometers can be used as colorimeters, but higher resolution spectral analysis has some valuable extra benefits. We'll examine them more in our next session, Calculating Color. With additional lamps, more filters, and hybrid instrument designs, the lines between colorimeters and spectrophotometer designs aren't as clear-cut as they once were, so I'll mix the words freely throughout the presentation. For now, the subject is instrument designs. Let's examine an important fundamental difference in color measurement instrument designs.
No, not that kind of geometry. The arrangement of lamp, sample, and detector. Geometries are identified using a specific shorthand, a number for an angle, and sometimes a letter for diffuse. The lamp position is always first. It's written illumination angle, then a slash, and then detection angle. Lighting geometry is important in measurement for the same reasons it's important in visual evaluations. Diffuse light minimizes effects of texture and gloss. Direct lighting shows them off. It emphasizes the differences in shape and texture. And those differences will show up in your color numbers. Here you see the effects of direct versus diffuse lighting on a sample with various surface gloss and texture. Notice the obvious differences in the lightness and darkness of the glossy sample. The sample color below the surface is identical. Both surfaces reflect the same amount of light. The difference is in the direction of the surface reflection. The glossy surface reflects most light at a regular angle, like a mirror would. We call that specular reflection, from the Latin word speculum, for mirror. The matte surface is less mirror-like. It reflects light in many directions. By extension, the word specular is used to describe lighting geometries also. Those that don't include Those measurements that don't include the mirror-like surface reflection are called specular excluded. Those that do are called specular included. Here's the geometric arrangement for reflectance measurements again. The lighting is direct. The object surface can reflect light regularly or diffusely. And here's the fancy schematic for measuring transmittance. Again, the lighting is direct. The light can be transmitted through the sample directly or diffusely.
Now, here's a geometry that uses a sphere as the light source. The lamp does not shine directly onto the object. The sphere is coated with a matte white powder to direct light onto the sample plane at all angles, simultaneously. Totally diffuse light, except where the lens is looking into the sphere. There is no light falling on the sample from that direction, so there can be no light reflected at a mirror-like angle to the lens. This is specular excluded geometry. Moving the lens off the sample normal makes specular included measurements possible. Opening a hole in the sphere opposite the lens prevents light falling on the sample at the specular angle to obtain a specular excluded measurement. This is a directional geometry. A detector at a sample normal and lamps at 45 degrees to that plane. Most 45-0 instruments use ring detectors to help mitigate repeatability problems with textured samples. 0-45 works like 45-0, just reversing the positioning of the lamps and the detectors.
Here's another design, a goniospectrophotometer. It's a big word, but it basically means a number of geometries, almost always directional, built into the single instrument. Some abridged goniospectrophotometers have fixed angles. Some can move the lamp or detector to any position. Some can move both. Most people call them multi-angle because it's a lot quicker. Usually these instruments are specular excluded, but with variable positions for lamp and detector, measuring specular reflectance is also possible. The data color viewport is also a directional geometry, approximating 0-45. We call it a light cabinet, 45-0. The detector is a camera and gives pixel by pixel colorimetric output in an image. Its geometry matches visual evaluations and is repeatable, comparing equivalent points and using the same lamps. But being a light cabinet, its geometry varies slightly overall because each lamp is at a slightly different position, and the lamp, the sample size, and the fields of view are large. There's a rule, another geometry lesson, is that they're not mixable. Pick one, pick the other. Making comparisons, making conversions between one and the other isn't possible. Getting agreement between multiple locations or multiple instruments requires agreement in the geometry. Transmission versus reflectance is one class of difference. Directional versus diffuse lighting is another. And the terms specular included, abbreviated SCI, and specular excluded, SCE, add precision and differentiate options on sphere D8 and multi-angle design. Remember, don't expect measurements made with one geometry to agree with those made using another. Here's a summary of strengths and preferences for different instrument geometries. Directional measurements, 45-0, are usually preferred final QV measurements, detecting both surface and internal color differences. Diffuse measurements, sphere instruments, specular included, are preferred for color matching, formulation, recipe prediction, showing more clearly internal color differences and minimizing the surface differences. I list 45-0 as being preferred for fluorescent samples, but there's a fair amount of debate over that recommendation. Sphere designs are routinely used successfully for optically brightened samples. Transmission is an opposite case. It's listed under sphere instruments, but it's just a more common option on sphere instruments. It's also possible to do using 45-0 geometry. It's just not a common option in color measuring instruments. Now, let's turn to spend a few moments looking at uncertainty in color measurement. Looking at call center records over time, the most common sources of error or disagreement between locations come from measurement procedure and environmental factors rather than user error or instrument fault. Accuracy. The agreement of a single instrument to standard reference instruments is fundamentally a matter of design and specification. When you're reading specs for color measuring instruments, take note of the light source, the geometry, and the monochromator, the spectral analyzer. Ensure they match. Also, note the color metric and the details of the test that generates the specification for repeatability and agreement. It's not unusual for manufacturers to use different metrics, CIE versus CMC's DE, or CIE 2000. Agreement tests are often in terms of an average difference over multiple samples and multiple measurements, sometimes including a maximum value for any single measurement in the test.
Diagnostics. Each manufacturer recommends regular maintenance and diagnostics to ensure proper function of the instruments. Regular calibration and a product like Datacolor Guardian use stable test samples, usually ceramic or porcelain tiles, to verify performance. Datacolor Guardian also includes automatic email and review of regular diagnostic tests by professional service technicians to help discover signs of any misbehavior and correct them early before they lead to product defects and unreliable color measurements. A survey of Datacolor service records showed adherence to yearly maintenance recommendations, including reference tile replacements and diagnostics, reduced drifts on the instrument 75 to 80% per year. Precision, the repeatability of a single instrument or lack of it, is most often related to color measuring processes and adherence to agreed upon procedures. Users of color measuring technology will find that checking one's measurement processes for precision in a single instrument, which is repeatability, or among a group, which is reproducibility, is easily done. Presuming one uses stable sample material, a recommended rule of thumb or goal is to maintain process uncertainty. An average color difference among attempts at or below the factory-specified inter-instrument agreement of the spectrophotometer models in question. Here's an overview of best practices to reduce and control color measurement uncertainty. Agree and document procedures. Train operators. Test to verify performance and compliance. Maintain factory-recommended maintenance and service, daily calibration, regular diagnostics, and annual service. Datacolor recommends routine calibration and a simple drift test. The green tile test that we include is done with the calibration every 8 hours. Train operators to check tiles and traps for cleanliness. Log the green tile results along with ambient temperature and relative humidity for maximum traceability as insurance against possible questions in the future.
Here's a checklist of considerations when you're defining measurement technique. Let's look at some real-world data showing how much these factors can influence a color measurement. For translucent samples, stacking or folding to opacity eliminates uncertainty due to sample thickness and color changes or variation in backings or substrates. Here are a set of color differences comparing stacks of 2 and 4 layers. Making multiple measurements, rotating samples, and averaging the different readings can help ensure you make a more representative sampling, especially for objects with texture, weave, or color variations. Here in this table, we compare an average of 2 versus 4 readings. Remember, a larger area measured is a more representative sampling. Avoiding aperture changes to save time can be a false economy. Notice that it takes 10 measurements using a 9mm aperture to give the same measured area as a single measurement using the 30mm one. If your instrument options includes interchangeable sample apertures, use the largest possible for the sample that you have. Here's a comparison of 2 and 4 measurements using a 9 and 20mm aperture on various textured textiles. Notice the more highly textured samples benefit the most from larger apertures and averaging more measurement spots. Remember, between readings, the rotation, 45 or 90 degrees with each measurement in an average series, especially for textured samples. Beware of mixing aperture sizes. It's not much of a problem with samples that are opaque at their surface, completely opaque coating, but for translucent samples, even stacked or folded to opacity, the differences can be huge. Here's a photo of a translucent plastic sample as seen behind 3 different apertures. This isn't just an issue for instrumental evaluation, it's obvious visually. The color of a translucent sample depends on the area illuminated. Here are the color differences and spectral curves of those 3 samples. The CIE 76DE values of 30 to 40, CMC's 13 to 16 units, wide variations in the spectral curves. Here are recommended practices for environmental conditioning of textile samples. Every object changes color with temperature. Many do the same with humidity changes. Colorants in coatings or embedded in plastic tend to be less sensitive to humidity. Paper, textile, powder, absorbent products, however, they're far more sensitive. How much can environment affect the color? Well, let's have a look. Here's one of the BCRA ceramic tiles, a common reference standard. You can see the measured changes over 9 minutes exposed to a temperature differential of 10 degrees Celsius. Looking at color changes as we vary temperature and humidity in a polycotton blend dyed in various shades, compare the first 2 columns to see the effect of humidity at 25 degrees and the second 2 at 30 degrees. The first and third columns show the effect of a 5-degree temperature change, as do the second and the fourth. 5 degrees, 10 degrees, maybe not that much from morning till noon, certainly not summer to winter. In this, we exposed 50 common industrial pigments to a 10°C change in temperature. Colder, then hotter. The average differences are shown here in a large font. Here's a summary of the best practices and recommendations that tips we've given so far. Divided into measurement, environment, and instrument. Document your technique, standardize your standard operating practices, and publish. Verify conformance and train your operators. For the environment, you can test if your samples are sensitive or if they vary with with temperature or with humidity. Condition the lab, condition the office, or there are special cabinets for conditioning the samples in any environment. For the instrument, calibrate regularly, do weekly diagnostics or biweekly diagnostics, have the manufacturer's recommended service, follow the recommended service program. Datacolor recommends yearly service. We strongly recommend Guardian Diagnostic for the Guardian product for diagnostics and fleet management. So there we have it. Our goals that we set out for this morning were at the end of our exploration of color as a measurement with tips and best practices for selecting instrument options, maximizing precision, minimizing uncertainty in color measurement. We have about 16 minutes, 16 minutes for questions or comments. Are you ready, Phil?
Sure am, Ken. First question we have is, what are the pros and cons between specular component included and specular component excluded measurements? In very broad terms, we use specular component excluded measurements to measure color as affected by other appearance factors such as texture and gloss. We use specular component included for color matching, and part of the reason for this is it negates the surface effects of texture and gloss to a large extent, but also when we're working with color matching algorithms, we're normally working with things like Kabelka-Monk theory, and I won't give you the math, but essentially we're using the percent reflectance at each wavelength to calculate the absorption and scattering coefficients. If I take a very strong color that can absorb light deeply, let's say like a phthalocyanine blue or a red dye, okay, the blue would absorb very deeply in the yellow wavelengths, the red would be highly absorbent in the green wavelengths. With the specular component being somewhere generally in the area of 3 to 5% reflectance, that means that my lowest reflectance value at 3 or 5%, if I get an instrumental variation of, say, 0.1, let's say specular component included, my lowest value is 4%. So I could go 3.9, 4.1. If I plug that into that Kabelka-Monk equation, the resulting value doesn't vary tremendously between what I get at 3.9 and what I get at 4.1. If I measure specular excluded, my maximum absorption value may drop down to somewhere below 1.0 reflectance, and a 0.1 reflectance variation there makes an enormous difference in the resulting K over S calculation. Makes it much too sensitive for what we're looking to do in color matching algorithms. Historically, as I said, we've used specular component included for color matching because of the surface, the matte versus gloss, texture versus untextured, and because of the resulting impact of small instrumental variation on the Kabelka-Monk calculation.
Comment about the UV component on a spectrophotometer. Yeah, it was sort of glossed over, wasn't it? Just a bullet point as another setting to check. In general, if you're measuring samples that do not fluoresce, they don't fluoresce. And all of the instruments that you're using have the option of using a UV cutoff filter, so 0% UV. Inter-instrument agreement will be improved by eliminating UV entirely. If you're measuring samples that do fluoresce, then calibrated UV is definitely going to improve your inter-instrument agreement compared to simply unfiltered xenon flash lamps. Although that does depend a bit on the lamps themselves. There's a whole now where you get your some differences as to where you get your UV calibration standards. That depends somewhat on the kind of product that you're measuring. But definitely for samples that have a fluorescent component or are optically brightened, or if you're not sure, you can't tell from looking under a black light, either measuring them with and without, or with full UV and no UV if you've got the option on your colorimeter or spectro, that would tell you if it's necessary or not. Remember, with each of these possible variations, either in procedure or in instrument settings for your specific samples, the instruments that you have can be used to determine how many measurements you need to make, what conditions, what the differences are. You can examine the spectral differences and the colorimetric differences. So if you suspect that 5 measurements may be better than 4, that UV calibrated may be showing something different than a UV cutoff filter. Try measuring the same sample in the same spot, and check for yourself. The instruments are exceedingly sensitive.
Okay, we have another question about what's the best approach for measuring fibers? And we touched a little bit on this without specifically saying fibers, but because of the surfaces, we normally take multiple measurements, an average reading, if you will. Depending on the type of fibers and how they're presented, if you were making, like yarn fibers, the most common method is to use a mechanical winder to put it on a card. This gets the orientation and the amount of tension on the fibers consistent. And generally, most people approach it from the standpoint of, I'm going to average 4 readings, and I'm going to reorient them after each read. So in other words, I'll take a read, reorient it 90 degrees off of that position, take another read. Do that again 2 more times. Basically, you're going to have 90-degree increment repositioning in each turn. This helps minimize any directionality caused by the winding process. Other types of fibers will require special handling. Sometimes on carpet fibers, you'll see that they're put into a holder that basically orients them so you're looking at a flat surface of the fiber sticking up, sometimes in a holder that would resemble a plastic pipe. Other types of fiber samples, such as fluff, are sometimes put into a compression cell, and there's a piston behind them that is regulated by air pressure to present a uniform surface there. This kind of ties in with the second question that we have in that list about should I reorient my samples each time? And the answer, of course, is yes. Otherwise, all you're doing is a reproducibility of read test. You're measuring the same position on the sample without reorienting it or moving it from side to side. You're just finding out, can I take 2 readings and get the same sort of reading each time, rather than my sample has a surface variation or an orientation variation that requires me to take those readings.
For those of you who are using data color instruments, it's possible to set the number of flashes independently of the whether you're making for each reading. So if you were interested in averaging 3 instrument flashes at exactly the same spot and the same orientation, you could accomplish that fairly easy just by setting the number of flashes to 3. Typically it's set to 2, and that gives more than sufficient. There's plenty of a safety margin with 2 flashes being averaged into each single read. So moving the sample, if its size supports it, moving the sample and changing its orientation will give you a better overall sampling of its color.
Okay, there was someone mentioned about the volume of our voices on this webinar. We are doing this remotely. I'm located in Charlotte, North Carolina. Kenny's somewhere in the wilds of Arkansas right now. We do apologize for any technical problem with that. Just so you're aware that this is a limitation of what we're doing right now. Okay. There's also a question about what's the ideal temperature and humidity to base your standard operating procedure on. I don't know if those slides showed the tests that were done, but normally it's what, 25 Celsius and how much humidity? 40%, Kenny? 40, 50?
Right. The part that intrigued me was the ASTM specification of plus or minus 1C, which is certainly possible with most thermostats. So it's not onerous, but whatever you're picking, like most parts of a specification, you don't have to use a specific measurement. You don't have to use a specific published standard if you and the people that you're wanting to get agreement with agree. You can pick 21, you can pick 22C, you can pick 23. But it's the variation and time that you're allowing the sample to acclimate, and that depends on the sample itself, its thermal properties and its size and thickness. There's a question about average lifespan of the units, and if they're functioning normally, is there a need to update them? Second part first. No, if they're functioning normally, there's no pressing need to update them, although there are occasionally firmware updates that increase capabilities, and sometimes other factors like updating a PC to use a newer operating system, and there's a sort of follow-on to drivers that are no longer supported may produce an artificial need. Average lifespan really depends on how well the instruments are maintained and the environment that they're deployed into. There are examples of 20 and 25 and some 30-year-old instruments still functioning the way they were. But like any business concern, there's a certain amount of time that an instrument can be supported and spare parts can be acquired. So but it's not unusual to have Datacolor instruments last 10 years. But in extreme, if there's high vibration, if there are large temperature swings, then you expect the lifespan to be shorter.
Yeah, hostile environments are the big factor here, and regular maintenance. We have customers who still contact us about instruments that we discontinued nearly 20 years ago, looking for parts. Then again, I've been in locations where the environment in the laboratory was so bad that airborne chemicals played it out on the sphere of the instrument, making it necessary to have it refurbished, recoated essentially. For the most part, they'll last forever, and as long as we can get parts, we can continue to maintain them, as part of our service. What happens is after, well, in this case, we have a generation of spectrophotometers that we will be phasing out service for this year, and we haven't made any of those instruments in 12 years. There's a question here about, should a gloss meter be used to control gloss instead of using specular component excluded measurements? And the answer is yeah. If you're looking to control gloss, a gloss meter is what you need. Our 45G, which is one of the instruments Kenny mentioned actually has a gloss meter built into it for that purpose. So you can be measuring the color, specular component excluded, and also get a valid gloss meter reading. Gloss control is extremely important, especially in visual evaluation. The person that Kenny and I first worked for when we came to work at what was then Applied Color Systems came to the company from Ford Interiors. And he told me that at the time when they would do a visual evaluation, they would first check gloss. And the gloss target was, let's say, whatever it might be, plus or minus 10%. So if it required a 60 gloss, plus or minus 6. If it was a 20 gloss, plus or minus 2. He said if it fell outside of that 10% variation, they could not do a visual evaluation. They needed to get the gloss back in the range it was supposed to be in before they did any visual evaluation. So yeah, the answer is if you're looking to control gloss, use a gloss meter.
Can I argue just a bit?
Sure.
You're correct, no question. But the answer depends on how you're defining gloss. If you're defining gloss as 60 degree gloss, 20 degree gloss, your gloss is defined typically as at a specific angle. If you're if you're using a 45-0 instrument, there are some things that you can do to measure the surface, but that's not one of the standard gloss angles. If you're
I'm sorry. When I use those values, Kenny, I'm sorry. When I would use those values, I was talking about gloss value, not geometry, not the
right.
angle.
I'm just saying that
Okay.
you can use spec in, spec out to get some correlate that you can call gloss. If you're using a diffuse, like a D8 geometry sphere, you can get something that's gloss-like, but it's not an official gloss standard.
That's correct. In our anyone familiar with our software, when they run calibration on our sphere instruments, would notice that your choices are specular included, specular excluded, and gloss. And gloss calculates a gloss factor. Okay, it's not a gloss meter equivalent. It's meant to be, but it's an approximation. And we use that in our software, particularly for retail house paint type products, where people are trying to match a color, and they come in and they say, I'd like to get this particular color, and I want it in a flat for the wall, a semi-gloss for the trim, and a gloss for the door. And because gloss and color are independent variables of appearance, what they're looking for is where the flat wall paint meets the semi-gloss, where the semi-gloss meets the gloss. They want the appearance to be all one color, which it wouldn't be if all they had taken was the glossy paint and added flattener to it. As you went from gloss to semi-gloss to flat paint, it would look progressively whiter.
There's a question, can the gloss component alone be measured with any instrument from a sample that has an uneven surface? I'd love to tell you yes, but the answer is no. The geography of the surface and the index of refraction of the fiber or the material or the resin in which pigments are embedded, or the fiber that are dyed, they're almost inseparable. You could imagine some destructive ways of changing the surface, but changing the surface geography, the microgeography, the macrogeography of the surface. But in any real sense, no, the two are completely tied together. Photons don't know why they're getting bounced around. They just know they're getting the directions being changed. You mentioned the BCRA tile changed color under different temperature, humidity conditions. Did I hear that accurately? Yes, you did. I mentioned the red BCRA tile specifically because it was a worst case. But any physical object changes its interaction with light when its temperature changes, whether that's noticeable or not. And certainly The neutral BCRA tiles, the other color BCR tiles, are less sensitive to temperature and not particularly sensitive to humidity as long as their surface is intact and they're properly sealed where they're cut. But humidity in a ceramic or a porcelain tile, if the surface is cracked or crazed, they begin to age very rapidly. Water inside the porcelain, inside the ceramic, is deadly. Once you have a scratched or a crazed tile, it's time to replace it. Do we have time for a couple more?
I think so.
How would you handle matching a solid color when given a translucent as a standard? I would be very careful about the aperture that I'm choosing. Again, I would recommend the largest possible. Translucent samples will appear darker the less of their surface that you illuminate. I'd then be very careful about the backing and what you're actually matching. If the backing has a strong color, that some of it's going to show through. So I'd ask the client to specify or to agree that if you could, that using this aperture on this background, and if you're using data color instruments, the aperture plates for the most part, those with selectable apertures, are removable. You could also make a mask yourself with heavy cardboard, or if you got a machine shop, you can make some metal masks to look and see how noticeable the effect is. The example in my, it's hard to tell from the photo, but in the example, that yellow plastic, how can I describe it? If I imagine making Jell-O with skim milk instead of water, that was about the translucency, and the thing was about 3/4 of an inch thick. So if lemon Jell-O with milk in it is any kind of an accurate color specification for you, that might tell you the haziness and the translucency of that sample that I used.
And to emphasize, what Kenny was, mentioned before, that background, whatever is behind the sample, will affect the reading. For example, when you buy a spectrophotometer brand new, the sample holder will have a silicone tape on there, which is a beautiful white, which is meant to be a little tacky so the sample doesn't shift around, which means it gets dirty, it gets scuffed. Okay, if your sample is translucent to any extent, take Kenny's yellow sample there. If you back that up with that white background, it's going to measure brighter than if you were to back it up, let's say, with the black light trap. Okay, that now becomes your target. You have two different colors there, one with a white background, one with a black background. It's not uncommon, and Kenny will bear me out on this, that if I was printing on brown paper bags like you have in the supermarket, and I was going to look for red printing on it, the color of the ink that we put on the brown bag would not be red necessarily, but it might be a lighter color because it's going to have a darker background that absorbs the ink down into it. So the background behind the sample influences the read, and that now becomes your target if you have no way of increasing the thickness of the translucent sample to a point where a background doesn't affect it.
Here's a great question. Which is closer to human observation, either CMCDE or CIEDE? I presume by CIEDE you mean the CIEDE star from 1976. The clear answer is for
available next week.
Yeah, well, tune in next week and the week after. We're going to talk about color differences next Tuesday. In the fourth webinar in the series, specifying color, we're going to talk about tolerancing equations a fair amount. that's sort of this, a question about if we cover measuring whites in another webinar. Next week we're going to talk about appropriate metrics for neutrals and high chroma colors or higher chroma colors. We won't get into a lot on single number indices, but we'll cover it in passing in a 30-minute webinar. In general, whiteness indices, if you're in agreement on the method, you're in agreement on, if you're talking about optically brightened white samples, then agreement on your reference fluorescent target. If you're using Gans Greaser, if you're using CIE, if you've agreed on the method and you've agreed on the instruments, and you're careful to use them only for things that are appropriately white, you can get some really strange results if you start measuring high chroma colors, blues and yellows, and looking at their whiteness indices. So, but it's fairly straightforward, maybe not so straightforward to get agreement on all the components. Question: weekly diagnostics. Weekly diagnostics. Do you mean using Guardian weekly? I don't know if I read any surprise in that question. Weekly diagnostics. You do a simple sort of shotgun diagnostic whenever you calibrate the instrument and you do the green tile test. So that lets you know that it's like doing a check weigh with a standard weight after you've tared your scale. Weekly, it really depends on how important the measurements are to you. If I was going to be doing some really critical work, I would do a diagnostic and make sure that my calibration techniques and my tiles and my traps and the spheres are all clean, and spiff up the instrument, spiff up the tiles, and be sure that everything's in working order if I'm expecting to keep these measurements for a long time. Weekly, maybe some people it doesn't fit their cost versus benefit equation. Bi-weekly may be enough.
Here's an easy question. For various textures of stucco, would you recommend specular included or specular excluded? Specular included.
Specular included. Did we say the same thing?
Yep. Standard condition, 25C, 50% humidity. Thank you, Ron. We have limited access to what else is on the PC. Okay, well, we'd like to thank you all for joining us. We hope to see you next Tuesday for Calculating Color, number 3 in this webinar series, where we'll discuss colorimetric evaluations using color coordinates, spectral measurements, strength, and process analysis. Thank you all for coming, and hope to see you again.